How mathematicians know if adding up an infinite list of numbers will eventually settle on a single, finite value or spiral out of control to infinity. When we restrict that list to strictly positive numbers, the behavior becomes entirely one-directional. The running total, or partial sum, can only ever increase. There are no negative numbers to cause oscillation or jumping around. This chart shows a sequence of partial sums, stepping upwards. Because they only increase, these series follow a strict rule. The series converges if and only if it has a ceiling. If we can prove this sequence of partial sums is trapped below a constant horizontal upper bound, we know it converges. The most direct application of this is the geometric series. As seen in theorem 3.26, when our ratio x is strictly less than 1, the series predictably converges to exactly 1 over 1 minus x. Knowing terms are strictly non-negative simplifies the analysis. The search for a specific limit is replaced by a search for any finite upper boundary. But what happens when the terms decrease monotonically but do so very slowly? For these stubborn cases, we rely on Cauchy's condensation test, shown here as theorem 3.27. The formula, the sum of 2 to the k times a sub 2 to the k, looks dense on the page. To see why it works, let's look at the first 8 terms of the classic harmonic series. Instead of analyzing terms one by one, we can compress them. We group the terms into exponentially growing blocks, a block of 1 term, then 2 terms, then 4, and so on. In a decreasing sequence, the first term of each block, a sub 2 to the k, is also the largest. Since there are 2 to the k terms in that block, multiplying the count by that first term gives us an upper bound for the entire group. This logic maps directly to the algebra in Cauchy's formula. Let's apply this test to the standard p series, 1 over n to the power of p. We substitute our term directly into the condensation formula. The fraction simplifies to the sum of 2 to the power of 1 minus p, all raised to k. For this geometric series to converge, its ratio must be less than 1. This only happens when the exponent, 1 minus p, is negative, meaning p must be greater than 1. Rudin presents a notoriously tricky example to test this application, the series of 1 over n times the natural log of n. Take a moment to pause the video. Substitute this series into the condensation formula, simplify the logarithm, and determine if the series converges. Let's walk through the resolution. First, the 2 to the k in the numerator and the 2 to the k in the denominator cancel each other out. Next, we apply the logarithm power rule, pulling that k exponent down. This leaves us with a constant multiplied by 1 over k. 1 over k is the divergent harmonic series, proving the entire original series diverges. The condensation test operates like a mathematical magnifying glass. It takes series that move too slowly to evaluate and compresses them into fast-moving geometric series, so their behavior becomes obvious. There is a common assumption when studying these problems that there must be a specific boundary sequence, a definitive line separating all convergent series from all divergent ones. Rudin illustrates why this is impossible by comparing two series that differ only by a squared logarithm. One converges while the other diverges. Because we can always squeeze a new series between any two existing ones, a single fixed boundary can never be defined. To solve these problems efficiently, rely on your 3 standard rules. 1. Bounded partial sums guarantee convergence. 2. Check the ratio against the geometric baseline. And 3. Use Cauchy's condensation test to accelerate slowly decreasing terms. These tests for non-negative terms provide tools to analyze series with alternating signs or vector-valued terms. If you found this breakdown helpful, consider subscribing for more step-by-step mathematical proofs.